All right, so let's see. I want to do a couple of things. First, I just want to review matrix multiplication. So it's always row into column. That is, if you have a row of n numbers and a column of n numbers, or maybe I'll call this, yeah, n, why not? Say this is A1, A2 up to AN, and this is B1, B2 up to BN. The way you multiply them is you just multiply the corresponding coordinates and add. So you have A1 times B1, A2 times B2, all the way up to AN times BN, and you add them up. So if you had the rows 3, 7, 8, minus 1, and the column 2, 0, 5, 9, that's going to be equal to 3 times 2 plus 7 times 0 plus 8 times 5 plus minus 1 times 9. So that's 6 plus 0 plus 40 minus 9 is 37. Right? That's multiplying a row into a column. And you multiply matrices if the number of columns of the first, say this is m by n, and this is n by p. So every row here has n numbers. Every column here has n numbers. So you can multiply the row into the column and you get a matrix which is m by p. So let me just do one example so it's a little bit clearer. 7, 1 minus 2, 3, 0, 5. So this is 2 by 3. Suppose I just multiply it by a 3 by 1 matrix. That's a column. 297. So this is going to be a 2 by 3. Sorry, a 2 by 1 matrix. That's a column vector with two numbers. This is going to be 7 times 2 plus 1 times 9 plus minus 2 times 7. And the second entry, you take the second column, second row into the first column, the only column. 3 times 2 plus 0 times 9 plus 5 times 7. So this is 14, 23, 7 times 2, 1 times 9 minus 2 times 7. 14 plus 9 minus 14 is 9. And this is 6 plus 0 plus 35 is 41. And if you look at this carefully, you'll notice that when you multiply this matrix by this column, what this also is the same as, I'll prove this in a moment, this is going to give you a certain linear combination of these columns. It's going to be 2 times the first column, 9 times the second column, 7 times the third column. See, what is that? 2 times 7, 3 is the vector 14, 6. 9 times 1, 0 is the vector 9, 0. 7 times this vector, this is just scalar multiplication of vectors. This is minus 14, 35. When you add these vectors, you get 9, 41. Exactly the same as that. And this is a general phenomenon. If you have, let's say, A is an m by n matrix, and you're multiplying that by a column vector, What is that going to be? So this is m by n. This is n by 1. You're going to get an m-dimensional column vector, right? M by n, n by 1. The n's cancel in a sense. You get m by 1. And what is this first coordinate going to be? It's going to be the first row into this column. So that'll be summation. J goes from 1 up to n, Aij, Cj, A1j. The second coordinate will be summation. It'll be the second row, A21, A22 up to A2n, times this column. So A2j, Cj. All the way down to the last coordinate, which is summation. J goes from 1 up to n. You're multiplying the last row into the column. That's summation Cj, Amj. So if you look at what this is, let's see, you have A times this column vector, C1 up to Cn. So that's this matrix Aij times the column vector. You get a vector where the first coordinate is C1 A11 plus C2 A12 up to Cn A1n. The second coordinate is C1 A21 plus C2 A22 up to Cn times A2n, all the way down to the last coordinate, which is C1 AM1 plus C2 AM2 up to Cn AMn. And if you look at that, that really is the sum of these n vectors. And this vector is C1 times A1 down to AM. And this vector is C2 times A11, A21 down to AM1. This is C2 times A12, A22 down to AM2 up to C sub n, A1n, A2n down to AMN. This is a linear combination of the columns of A. So this is really a very fundamental point that you just need to remember all the time. When you take a matrix times a column vector, that gives you a linear combination of the columns of the matrix. And the exactly analogous thing is true if you take a row vector times the matrix. Now, how can you do that? So if A is your m by n matrix, you can multiply it on the left by a row vector. This is going to be, this has one row and m columns. This is a 1 by m matrix. Right? A column is a n by 1 matrix. A row is a 1 by m matrix. One row, m numbers. And here you have your matrix. So this is 1 by m, that's the row. This is m by n. This is the matrix. So the result is going to be a 1 by n, an n-dimensional row vector. And you get exactly the same result, and it's all written out carefully in the new set of notes that I have to put up this afternoon. When you multiply a row vector into a matrix, this row vector that you get is a linear combination of the rows. Its summation, I goes from 1 up to m, c sub I times the ith row of A. And the best way to understand this, and I think really the only way to understand this, is just to write down some matrices and some vectors and do this left and right multiplication of your matrix by a vector and see exactly that it is this linear combination of the rows and the columns. So let me just summarize that again, or just say it again. If you have A is an m by n matrix, that's the first row. The ith row would be AI1, this is AIJ, up to AIN, down to the last row, AM1, AMJ, up to AMN. If you take the ith row of the matrix, so that's row sub I of the matrix, this is just this row vector, AI1 up to AIN. It's an n-dimensional row vector. And if you take the jth column, this is the jth column of A, which is A1J down to AMJ. So you have, in an m by n matrix, you have m different rows and n different columns. And if you take the vector C to be a column vector, C1 up to Cn, then the matrix A times this column vector is a linear combination of the rows of the matrix. Sorry, it's a linear combination of the columns of the matrix. Summation J goes from 1 up to n. For each of the J columns, C sub J times the jth column of the matrix. And if C is a row vector, C1 up to C sub m, then CA, so that's C1 up to Cm times the matrix, this is a certain linear combination of the m rows of the matrix. I goes from 1 up to m, C sub I times the ith row of A. So this is an extremely valuable way to understand matrix multiplication. In matrix multiplication, you may multiply a matrix by a column vector. You get a linear combination of the columns of the matrix. You multiply a row vector times the matrix, you get a linear combination of the rows of the matrix. Okay? So that is a useful fact. What are some more useful things about matrices? Well, remember the elementary row operations on the matrix. What are they? You can interchange two rows. So maybe you interchange row K and row L. Now, there's the second elementary row operation is multiply your row, say row K, by a scalar that's different from 0. And the third elementary row operation is you add a multiple of one row to another row. So for K different from L and C non-zero, add C times row K to row L. Those are the three elementary row operations on a matrix. Now, what is called an elementary matrix is a square matrix obtained from the identity matrix. The identity matrix, which I always denote by I, is the matrix which has 1 down the main diagonal and zeros everywhere else. So an elementary matrix is a matrix that you get from the identity matrix by performing one elementary row operation. So for example, for n equal 3, the identity is 1, 1, 1 down the main diagonal, and the other 6 coordinates are 0. Suppose we interchange rows 2 and 3. So the first row is the same, but we interchange the second and third rows. We get 0, 0, 1, 0, 1, 0. So this is an example of an elementary matrix. Suppose we multiply row 3 by C. So 1, 0, 0, 0, 1, 0. And the third row, 0, 0, 1, when you multiply it by C, becomes 0, 0, C. So this is another example of an elementary matrix.
Professor, I have a question.
Yes.
After this, are you gonna be doing a review?
Oh, yes.
Okay.
Yes.
All right, thank you.
And the third elementary row operation is adding a multiple of one row to another. So if I add C times row 3 to row 2, what do I get? I start with the identity matrix, and I'm not going to change the first row, and I'm not going to change the third row. But if I multiply the third row by C and add it to the second row, I get 0, 1, C. So these are the three types of elementary matrices. They're an elementary matrix, again, is a matrix you get from the identity matrix by performing one elementary row operation. Now, This is important because we can describe each elementary row operation on any matrix in terms of an elementary matrix. So suppose, for example, in a matrix A, we want to interchange rows 1 and 2 in the matrix A. If you take the matrix A and you multiply it on the left by the elementary matrix that you get by interchanging the first 2 rows. So this elementary matrix, for all the rows from the 3rd on down, it doesn't change. But when you interchange the first 2 rows, the first row becomes the second, and the second row becomes the first. So this is your elementary matrix that you get by interchanging the first 2 rows. What happens when you multiply that times A? Well, we just observed that every row vector times a matrix is a linear combination of the rows of the matrix. How do you get the first row of the matrix of this product? You multiply the first row into A. That's a linear combination of the rows of A, but this means 0 times the first, 1 times the second, and 0 times all the rest. So what you end up over here is row 2 from matrix A. Here you end up with row 1 from matrix A, but all the rest are unchanged. So multiplying this elementary matrix times A interchanges the first 2 rows of A. And you have a similar phenomenon with all the other elementary row operations. So we have the following fact that a sequence of elementary row operations on a matrix A is exactly the same thing as A multiplied on the left by a sequence of elementary matrices. So you have your matrix A, you multiply it by an elementary matrix, and then another, however many times is necessary in order to put A in reduced row echelon form, and you have the following statement. So if A, after a sequence of elementary row operations, gives you a reduced row echelon matrix R, then there's a sequence of elementary matrices E1 up to E sub L, where this product times A equals R. Right? So that's the important fact that I wanted to bring forth right now. Okay. Any questions about this? Okay. If not, let's go look at the review sheet. I can do them in any order. I mean, I can start with the first and go through to the last, which is number 14. Or if you have a preference for one you want to see right away, let me know and I'll do that first. Okay, well. Then I'll do them in order. So these are review problems. So number one was to find the solution space of the equation 8x minus 9y equals minus 20. So there are lots of ways to do that. One is, for example, this is what you did in high school. This is the same as saying 9y equals 8x plus 20. So for any x, y is going to be 8/9 x plus 20 over 9. So if the vector xy is the solution of this equation, then y is equal to 20 over 9 plus 8/9 x, which is the vector 0, 20 over 9, plus the vector x, 8/9 x, which is 0, 20 over 9, plus x times the vector 1, 8/9. Or if you like, this is the vector 0, 20 over 9, plus x over 9 times the vector 9/8. So the solution space is, let's say W, it's 0, 20 over 9, that vector, plus the set of all vectors of the form x over 9 times 9 over 8 for any real number r. But of course, as x runs through all the numbers, so does x over 9. So I can make this slightly simpler. It's not necessary, but it's just aesthetically more pleasing. This is 0, 20 over 9, plus all multiples of the vector 9/8. So this is the, actually, I'll call this L. So this is the affine space of all solutions. Actually, to be very careful, what I did is show that any solution is going to be in this space. On the other hand, you can check that every vector of this form is a solution. So this is, in fact, the space of all solutions. Okay. Any questions about that? And this is the form in which the answer should be given, right? As a subset of the vector space R2.
I was gonna ask, would we need to put the 2 in like the on top of the R? Do you know what I'm talking about? Or can we just leave it as R when we put X and R?
Well, no, R2, if you write R2, that would be wrong.
Oh, okay.
This is what the real numbers are. So
Okay.
this set L is contained in R2. It's a set of two-dimensional vectors, but X itself is just a real number. So this is R and not R1, not R, not R2. L, set of vectors, is in R2, but this is just the number X. Just the way 9 is a number, it's not a vector.
Thank you.
Would it just be x, or would it be x over 9 times the vector?
Well, I just said that if you look at all numbers of the form x over 9, that's the same as the set of all numbers x, right? Because if you give me a number like 17, 17 is also 17 times 9 over 9. It's the same thing. If you leave it like this, it's correct. If you write it like this, it's correct. They're both correct. It's just a matter of choice.
Okay, thank you.
Right. The important thing is not to write down something that is incorrect. So problem 2, we have one equation in 3 variables, 2x plus 11y, minus 11y. Plus z equals 7. And again, if you look at this equation, you can say that 7 that z is 7 minus 2x plus 11y. So you give me any numbers for x and y. If I let z be this number, then x, y, z is a solution of this equation. But z has to be 7 minus 2x plus 11y. And if I write this in a nice way in terms of vectors, this is 0, 0, 7 plus x0 minus 2x plus 0, y, 11y. Right? Again, you add these three vectors, this is what you get. And this is 0, 0, 7 plus x times the vector 1, 0, minus 2 plus y times the vector 0, 1, 11. So the solution space is the vector 0, 0, 7 plus the set of vectors that are linear combinations of 1, 0, minus 2 and 0, 1, 11 for all x and y in R. So this is an affine subspace of R3. Right? That's the answer. And problem 3, this is just to calculate a linear combination of vectors. I have
Wait, sorry, Professor. You
sorry,
I want to ask a question.
go ahead.
You see that C and underscore next to the R3. What does that sign mean?
This?
Yeah.
Oh, so to say that, so it's like this. This means the set X is a subset of the set Y. That's just standard notation about sets in any kind of mathematics.
Okay, thank you.
So I have minus 1, 0, 1, 2, 3. I have times 8 plus 3 times the vector 4 minus 7 minus 5, 1, 1, minus 2 times the vector 7 minus 8, 0, 1, 9. So 8 times this vector is minus 8, 0, 8, 16, 24. This vector is 12 minus 21 minus 15, 3, 3. This vector is 7 is 14 minus 16, 0, 2, 18. So when I add, I get minus 8 plus 12 is 4, minus 14 is minus 10, minus 21 plus 16 is minus 5, 8 minus 15 is minus 7, minus 0 is minus 7, 16 plus 3 is 19, minus 2 is 17, and 24 plus 3 is 27, minus 18 I think is 9. So if I did arithmetic correctly, this is the answer. Right? All right. Problem 4. So in R3, we have the following three vectors, 0, 1, 1, 1, 0, 1, and 1, 1, 0. And we want to show that every vector is a linear combination of these three. That is, so given, let's say x1, x2, x3, find a vector T1, T2, T3, or maybe I'll call, well, it doesn't matter what I call it, such that x1, x2, x3 is T1 times F1 plus T2 times F2 plus T3 times F3. I want to be able to, these are the equations where the unknowns are the T1, T2, T3. So let's just expand this. What does this mean? If I have T1 F1 plus T2 F2 plus T3 F3, that's T1 times F1 is 0, T1, T1. And T2 F2 is T2, 0, T2. And T3 F3 is T3, T3, 0. When I add, I get T2 plus T3, T1 plus T3, T1 plus T2. And the question is, can I find numbers T1, T2, and T3 such that this equals x1, x2, x3? That means I have to solve the following system of equations. T2 plus T3 equals x1. T1 plus T3 equals x2. T1 plus T2 equals x3. So this is 3 equations and 3 unknowns. And I can solve it any way I like. I mean, I could do it the way I did in high school, just by adding and subtracting equations. Or I could use the augmented matrix. So since we're doing linear algebra, let me do that. What's the augmented matrix for this system of equations? The coefficients of the t's are 0, 1, 1, 1, 0, 1, 1, 1, 0, and you augment it with the right-hand side. So this is the augmented matrix. And then we want to put this in reduced row echelon form. So let me do that. Well, I'll do it here and see if it fits. I'll interchange the first 2 rows, 1, 0, 1, x2, 0, 1, 1, x1, 1, 1, 0, x3. And then I'll take the first row and not change it. I'll take the second row and not change it. But I'll take the third row minus the first row. So I get 0, 1, minus 1, x3 minus x2. And now my first row starts with a 1, and everything in that column is 0. My second row starts with a 1. This is 0, but I need to get a 0 down here. So I'm not changing the first row. And I'm not changing the second row now. But I'm taking the third row minus the second row. So that gives me 0, 0, minus 2, x3 minus x2 minus x1. And then I want to get a 1 here. So I have 1, 0, 1, x2, 0, 1, 1, x1. And I just multiply this row by minus a half. So I get 0, 0, 1. So I'm dividing by minus a half. I get x1 plus x2 minus x3 over 2. And then I need to get zeros here and here. So I have 0, 1, 1, x1, 0, 0, 1, x1 plus x2 minus x3 over 2. If I take the first row minus the third row, I get 1, 0, 0. This minus this is x2 minus x1 minus, so I get this minus this, I get x3 minus x1 minus x2 over 2. That's this minus this. Minus x1 over 2 plus x3 over 2 minus x2 over 2. Okay, good. And then to get a 0 here, I have to take the second row minus the third row. So I get 0, 1, 0. And this minus this is minus x1 over 2 minus x2 plus x3 over 2. So I don't know if this is correct, but this is certainly the right method. And this set of equations is equivalent to saying T1 equals this, T2 equals this, T3 equals this. So T1, T2, T3 is x3 minus x1 minus x2 over 2 yeah. Let me just double check because I know there's some little mistake here in the arithmetic. So let me just go through this again. In fact, I'll just do it again. So if x1, x2, x3 is going to be a linear combination of the vectors f1, f2, and f3, that's this system of equations. T2 plus T3 is x1. T1 plus T3 is x2. T1 plus T2 is x3. So this gives us in reduced echelon, when we look at the augmented matrix, we get 0, 1, 1, x1, 1, 0, 1, x2, 1, 1, 0, x3. And we need to row reduce this matrix. So I interchange this first and the second rows. And then I take the third row minus the first row. 1 minus 1 is 0. 1 minus 0 is 1. Minus 1, x3 minus x2. And then I have my first row, which looks good at the moment. My second row looks good at the moment. But I want to get a 0 here, so I subtract row 2 from row 1. So 0 minus 0, 1 minus 1 is 0. Minus 1 is minus 2. x3 minus x2 minus x1. And then I want a 1 here. So I have 1, 0, 1, x2, 0, 1, 1, x1. Divide by minus 2. I get x1 plus x2 minus x3 over 2. And then I want zeros here and here. So let's start with the first row. The second row I'm not changing. The third row I'm not changing. But I take the first row minus the third. 1 minus 0, 0 minus 0, 1 minus 1, that's 1, 0, 0. And this minus this gives me minus x1 over 2 plus x2 over 2 plus x3 over 2. And then the last step is to get rid of this 1. So I have 1, 0, 0 minus x1 plus x2 plus x3 over 2, 0, 0, 1, x1 plus x2 minus x3 over 2. I take the second row minus the third row. 0, 0 minus 0, 1 minus 0, 1 minus 1. Gives me 1, 0, 1, 0. This minus this is everything over 2 is going to be minus x1 minus x2 over 2 plus x3. So this corresponds to the set of equations T1 equals minus x1 plus x2 plus x3 over 2. T2 equals minus x1 minus x2 plus x3 over 2. And T3 equals x1 plus x2 minus x3 over 2. So if I take 2t, t2 plus t3, the x1 and x2's cancel. Yeah. So this is supposed to be x1, but, and I know this should be a plus here. So why don't I get a plus here? That's what I want to know. Oh, x1 minus this is plus. That's right, good. That's what I needed, plus. So, no, that's plus. So T2 plus T3, T1 plus T3, T2, T1 plus T2. So T1 plus T2 is x3. T1 plus T3 is x1 plus x2. So I know I have the signs wrong here somewhere. Let me just see why. So 1, 0, 1, x2, 0, 1, 1, x1, 1, 1, 0, x3. So 1, 1, 1, 0, 1, x2, 0, 1, 1, x1. Subtracting the first row from the third, I get 0, 1, minus 1, x3 minus x2. 1, 0, 1, x2, 0, 1, 1, x1, 0, 1. Now I'm going to subtract the second row from the third. So I get 0, 0, minus 2, minus x1, minus x2, plus x3. And then I divide by minus 2, x1 plus x2 minus x3 over 2. So this I'm sure is correct. Then I subtract the third row from the first row. So 0, 1, 1, x1, 0, 0, 1, x1 plus x2 minus x3. x2 minus this is minus x1 plus x2 plus x3. And I subtract this from this, so it's this minus this, is minus x1 minus x2 plus x3. So if I add, so then this should be t1 is minus x1 plus x2 plus x3. Yeah, something still doesn't right. If I add t1 and t2, I get x3. If I add t2 and t3, it doesn't work. And if I add t2 and if I add t1 and t3, if I add t1 and t3, the x1s cancel, the x3s cancel, and I get x2, that's good. But if I add x2 and x3, yeah, something isn't right here, and I'm not sure what it is, but I don't want to spend more time on this problem right now. I'll fix it up. I may just do one more of these now, and I'll do the rest this afternoon. This is problem number 5. Problem number 5 is prove that the set W, which is all vectors x, y in R2, such that 3x minus 2y equals 0 is a subspace. So suppose you have vectors, say x1, y1 in W and x2, y2 in W. So this means that 3x1 plus minus 2y1 is 0, and 3x2 minus 2y2 is 0. If you add these equations, you get 3 times x1 plus x2 minus 2 times y1 plus y2 is 0 plus 0 or 0. So x1 plus x2, y1 plus y2, this is a solution of the equation, so it's in W. But this is the same as x1, y1 plus x2, y2. So W is closed. Under vector addition. And if you take 3x1 minus 2y1 equals 0, and you multiply it by c times 3x1 minus 2y1, which is 3 times cx1 minus 2 times cy1, that's just still c times 0, which is 0. So cx1, cy1, which is c times the vector x1, y1, is in W. So W is closed under scalar multiplication. Also, I should observe that 3 times 0 minus 2 times 0 is 0. So the 0 vector is in W. So the 3 conditions for a vector subspace are satisfied. W contains 0, is closed under vector addition, and is closed under scalar multiplication. So W is a vector subspace. What does it look like? What is the picture of that subspace? So if you look at all the vectors x, y, where 3x minus 2y equals 0, this is the same as the equation y equals 3 halves x. So as they taught you in preschool or somewhere, this is just a straight line through the origin whose slope is 3/2. And suppose you look at the affine subspace 2, 0 plus W. Well, this is the vector 2, 0. And if you add 2, 0 plus W, so this is just shifting this line up 2 units. So this is 2, 0 plus W. It's a parallel line with y-intercept 2. So if you take 2, 0 plus xy, that's 2 plus xy. That's that vector. And if 3x minus 2y is equal to 0, because xy is in W, then 3 times so 3x minus 2y is equal to 0, then let's see, how do I want to say this? 3x minus 2y equals 0 means y is equal to 3/2 x. So 2 plus xy is 2 plus x 3/2 x. Actually, we're just getting the same thing, of course. This is 2, 0 plus the same vector. It's just this set of points shifted upward 2 units, adding the vector 2, 0 to it. But the whole point of this exercise is that in 2 dimensions in R2, a vector subspace is just a line through the origin. An affine subspace is any line. So every line is parallel to some line through the origin, and that's what the affine subspace is. So in problem 4, I have the vectors 0, 1, 1, 1, 0, 1, and 1, 1, 0. And I want to show if I take any vector x1, x2, x3 in R3, I can write that as T1, F1 plus T2, F2 plus T3, F3 for some unique numbers T1, T2, and T3. So this is T1 times the vector 0, 1, 1 plus T2 times the vector 0, 1, 0, 1 plus T3 times the vector 1, 1, 0. So when I add, I get T2 plus T3, T1 plus T3, T2 plus T3. So this gives me a set of linear equations to solve. So I want to solve the system of equations T2 plus T3 equals x1, T1 plus T3 equals x2, T1 plus T2 equals x3. So I write down the augmented matrix for these linear equations 0, 1, 1, x1, 1, 0, 1, x2, 1, 1, 0, x3. And now I want to put this in reduced row echelon form by a series of elementary row operations. So the first will be to interchange rows 1 and 2. And the next will be to subtract the first row from the third row. So 1 minus 1 is 0. 1 minus 0 is 1. 0 minus 1, x3 minus x2. And then the next step will be to get a 0 here. So the first row I'm not changing. The second row I'm not changing. But then I take the first row minus the second. So I get 0. 1 minus 1 is 0. Minus 1 minus 1. And x3 minus x2 minus x1. So my first column is good. My second column is good. I want a 1 here. So the next step, I have 1, 0, 1, x2, 0, 1, 1, x1. Divide this by minus 2. I get 0, 0, 1. I get x1 plus x2 minus x3 over 2. And now I need zeros here and here. So I take the first row minus the third. 1 minus 0, 0 minus 0, 1 minus 1. x2 minus this, I get minus x1 plus x2 plus x3 over 2. And then I want to get a 0 here. So 1, 0, 0 minus x1 plus x2 plus x3 over 2. 0, 0, 1, x1 plus x2 minus x3 over 2. And to get a 0 here, I subtract row 3 from row 2. 0 minus 0, 1 minus 0, 1 minus 0 is 1. 1 minus 1 is 0. x1 minus this is x1 minus x2 plus x3 over 2. So this tells me that the solution to my system of equations is T1 equals minus x1 plus x2 plus x3 over 2. T2 is x1 minus x2 plus x3 over 2. T3 is x1 plus x2 minus x3 over 2. So how do we check if this is correct? What we have is that or what we need, I'm going to take a bigger piece of paper, is that the vector x1, x2, x3 is supposed to be this linear combination T1, F1 plus T2, F2 plus T3, F3. And here are my values for T1, T2, and T3. So this is minus x1 plus x2 plus x3 over 2. That's just a number times the vector 0, 1, 1 plus x1 minus x2 plus x3 over 2 times the vector 1, 0, 1 plus x1 plus x2 minus x3 over 2 times the vector f3, which is 1, 1, 0. So when I collect all of this, the first coordinate is this plus this, x1 minus x2 plus x3 over 2 plus x1 plus x2 minus x3 over 2. That's the first coordinate. Second coordinate is this plus this. And the third coordinate is this plus this. And when I add, I get x1 over 2 plus x1 over 2 is x1. The minus plus x2 plus x3 is just x1. Here, the x1s cancel, the x3s cancel, and I have x2. Here, the x1 and the x2s cancel, and I have x3. So this is correct. This checks out perfectly. So what I proved is that if the vector x1, x2, x3 is a linear combination of f1, f2, and f3, the coefficients must be these. And in fact, these work. So every vector in R3 is a unique linear combination of those three vectors. So good, I'm done. Any questions? Sometimes you just have to do things carefully. Okay, that's it for now.